Happy LDoc, everybody. We've made it to the last lecture of Comp 110. Today we're going to be looking at painting with a special graphics library called a Turtle graphics library, and we're going to be making some art together. So we're going to introduce a very simple graphics library called Turtle Graphics, and this is something that has been around since the late 60s. It came out of MIT. And many people have come up learning how to program with Turtle Graphics. And one of my first programming experiences was with Turtle Graphics. And so I wanted to share that with you today as well. What we're going to do is we're going to use some very simple functions that are going to move a virtual and invisible turtle around on the screen. And that turtle will be dragging a marker by its tail is how you should think about it. So what are the four functions that we have available to us? Well, we can move the turtle forward by some number of pixels or some distance. So if we imagine a very poorly drawn turtle, right? So here's my turtle, and now you can see why I went into computer science and not art. If we said forward by some number of pixels, it's going to bring the turtle forward, and as the turtle goes forward, it's going to leave a trail behind it, right? So we're drawing a line with this turtle as if it had moved forward by some amount. And then the turtle can turn either to its left or to its right. And we're not going to see these turns, but after a turn, if we move forward again, like let's say we moved, we turned to the right by 90 degrees and then moved forward again, we could draw the corner of a square. We'll see that there's another function named move to that would cause the turtle to magically transport to some other position on our white canvas. Right? So these are the four functions we have available, and using these functions, we're going to start to express bigger concepts, more abstract concepts in terms of these simpler operations that we can ask our turtle to do. So I'm going to have you open up the next example in today's lecture material, and it's the OO Square app. So the turtle turns in terms of radians, right? So we can, if we wanted to turn 90 degrees, we can divide pi by 2, and that will turn the turtle by 90 degrees. All right, so we've got a main function here and our library functions imported. And then we have our blank canvas because I've run npm run start to begin the development server. So before we draw a square, let's see if we can just draw a line of 100 pixels. So I'm going to call the forward function with 100. And notice that the turtle slowly moved across the screen, dragging out a line behind it. Right? And if we wanted to turn the turtle left by 90 degrees, we could say left and math.pi over 2. Right? So pi over 2 is 90 degrees expressed in terms of radians, right? And so forward 100 again, and let's see if we've turned a corner. And so sure enough, we've turned a 90-degree angle. And when we move forward again by 100 pixels, we've brought out another side to our square, right? So we could continue doing this, right? And I could copy this, and if I wanted to, I could copy this, and if I wanted to, I could just repeat this a few times. And sure enough, we've got a turtle that's moving around, and we're drawing a square, right? And I've actually drawn an extra end of my line here. I didn't need this last forward. But notice that there's repetition here, and there are some hard constants that we've defined in here, like this 100 is repeated, and that data is repeated 4 times. Same with this math.pi over 2. And so one of the things that we've learned this semester is that when you find yourself trying to express an idea, if this idea of making a square, these are the steps that we can ask the turtle to carry out one by one. But if we wanted to make a bunch of squares of different sizes and maybe move them to different areas or locations, this would get pretty repetitive pretty fast. And so what is a strategy we can take to simplify our code a little bit? Well, one of the things I want to point out, because we're going to make use of this in the next example as well, is there's one process here that's getting repeated 4 times, right? This idea that we're moving forward by 100 degree or 100 pixels and then turning left by 90 degrees. So what if we defined a function named forward turn? and we're going to give it a width parameter or a distance parameter. And that distance will be a number. And this will be a void function. This will just be encoding a couple of steps to make a forward turn, right? And so what is going to go into a forward turn? Well, we've seen 4 of those here. So I'm going to just take one of them and cut it and paste it down below, right? And now notice that I can re-implement my main function by saying forward turn, and then 100 pixels is the distance we're going to give it. And we can do that 4 times. So let me copy that and paste it 4 times. Okay. And I'm going to try that, and I'm going to save it. And notice that now I've simplified my main function a little bit. Okay, so we're moving forward and we're turning, and we're moving forward by 100. Well, if I change this amount to, let's say 10, I wanted to make a much smaller square here, so I could delete the zeros on each of those lines. Notice that we didn't change size because I didn't actually update the forward by 100 pixels function call down in this forward turn function. So we want to make that the distance parameter here. And one of the big concepts of functions, and there we go. As soon as I save that, notice we have this smaller square. One of the big concepts of functions is that we can set up parameters that allow us to have one function that takes an extra bit of information. In this case, the parameter is distance. And now we can make these function calls using different distances that we plug in from the point of the caller. We don't have to hard code these numbers into the function definition, right? So this is a minor improvement, but what if we wanted to just have, how can we create the idea of a square? Well, we can set up another function named letSquare be defined in terms of a side length, and that will be a number parameter and void, right? And if we wanted to be very straightforward about this, we could just copy these 4 lines and paste them here. And notice once again, we've hard-coded 100 in to those calls, but now that we have a function and we have a parameter, we should substitute that parameter instead so that we can actually draw squares of various lengths, right? And if I go and now say, okay, my main function is draw a square of length, let's try 50 this time. Notice we were able to make a simple square of 50 pixels. That's pretty cool. We learned about loops early in the semester, and that means we don't have to copy and paste lines here. Now, having 4 calls to forward turn isn't the worst thing, but if we wanted to remind ourselves of a for loop, we could set up a for loop here that will run 4 times and use I as its counting variable. And then what we're going to do inside of that for loop is just simply make a forward turn by the length parameter. And so notice that as we are expanding and defining these functions, we're able to start thinking at a higher level, right? So main has this, is drawing a square of 50 pixels. Well, what if we wanted to be able to draw squares of different sizes at different locations? Well, we could set up an X parameter and a Y parameter, right? So now we add 2 parameters to our square. And I can call this with, let's just say 100. 100 is going to be the X and the Y. Remember, our X coordinate axis is from 0 in the top left and increases as we move to the right. Our Y axis is from 0 and increases as we move down. So the Y axis is inverted. And so we've added these parameters, but we haven't actually taken the action inside of square to move the turtle to some other location. And in order to do that, we need to import the move to function. Right? So this idea that we can import functions that are defined elsewhere, right, means that we can reuse some functionality from other locations and use libraries. And so I'm going to move to the X and the Y position that is passed in. And so now when I save this, notice that the turtle is up closer to the top left. And now if I wanted to, I could draw a square that was, say, at let's try 200, and we'll make it 25 pixels wide, right? So there's my first square, and there's my second, right? We could parameterize these things if we wanted, and we could make, if we wanted to just explore this, let's say we wanted to make 10 squares on our screen. I could set up I to be 0 and say I is less than 10, I plus plus, and we could draw a square. And maybe we do, for the x, let's say I times 10, or let's do I times 20, I times 20 for the y. So these will be moving in a diagonal direction because we're increasing the x and the y that we start at. And let's do, maybe we'll make these increase in size. So I times 10 again. So the first one will be 10 pixels. Actually, let's start from 1 instead of 0 because it would make no sense to have 0 times 10 as the width of our square. So we try this out. And here come my squares. And notice that we are taking some very simple functions and combining them back together in order to express higher level, bigger picture concepts. And this is really what the idea of abstraction in computer science is all about. What I want to encourage you to recognize here is that we're arbitrarily slowing the computer down in order to be able to see what it's doing, right? The computer could do this much faster than what we're seeing here. And in fact, if we were to set this speed to be a little bit faster, so set speed as a function of our Turtle graphics library, we can see that it can move much faster, but in fact, that's still arbitrarily slowing it down by a significant amount. If we were to do number dot max value, we would see that the program, as soon as I refresh it, it draws it immediately, right? So if you think about all of the steps that are going into a little piece of art like this, or a little drawing like this, graphics that are coming together, we can think about how these very simple ideas, right? All this Turtle is able to express is the ability to go forward or turn left or right and move to some other location. But using those very simple primitive capabilities, we were able to make something that was higher level and more expressive and build in terms of those, right? And then we invented the idea of what a square was. A square is you give me two numbers, and that's going to be where I'm going to move my marker to, and then the width of my square, and I'm going to be able to draw that. Right? So we're going to take this and move to a hands-on, and how can we think about trying to draw maybe a recursive spiral using Turtle graphics? In this next hands-on, I want you to try drawing a spiral. And the logic for the spiral will be recursive. It will be defined in terms of itself. So if we take a look at the spiral example, you'll see that there's not much here. Right? We've got a main function that's dispatching off to the spiral function with a call where the width will be 100. And your goal is to try and draw a spiral. Where we're going with this is a spiral that's going to look something like this, right? So if I start on one side, we'll be spiraling in this way, right? And it will be a much better looking spiral than I can draw by hand. But effectively, we're going to be continuing to draw lines or sides of a spiral and decreasing the length of those lines each time we make that 90-degree turn. And that will cause us to move more and more inward until we reach some point that we're going to need to stop spiraling, right? And so I'm going to leave this one to you. I want you to try and implement this spiral yourself. This is an example of recursion being applied in a graphical context. And see if you can make it work. Pause the video here and resume back once you're ready to continue. All right. So hopefully you were able to get that spiral going, and it's pretty fun to see recursion in action in a graphical sense. What we're saying here is we're going to move forward by the width parameter amount, right? So if I save, we can see that, okay, sure enough, there's our turtle. It's moving forward. And then I can try and turn left by math.pi over 2. And that is our left turn. We won't see that if I tried to save it because the turtle is invisible. But the next time we call forward, we'll be moving forward from this position. And then what we're going to do is add a conditional here and say if the width is greater than 10, then what we are going to do is the same process repeated. Right? We're going to spiral again. But notice that if we spiraled again, and I just gave width here, right, we would have a problem. So what happens when I do this? Well, eventually, if I were to look in my browser's console, we would see that we have a call stack exceeded error, right? So I've got stack overflow, right? We've called this recursive function infinitely many times, or at least as many times as the computer could before running out, which isn't anywhere close to infinity, right? It's probably somewhere around 10,000 times this function got called before the computer gave up and said, hey, it looks like you've got infinite recursion here. So we need to do something in order to avoid this infinite recursion, right? And so if we jog our memory and we think about, well, how do we avoid infinite recursion? We need to be moving our recursive case closer to the base case. And that actually brings about something interesting here. The way this function is written, there's not an explicit base case, right? So I'm going to come back and address that, and we can rewrite this function to have a base case shortly. But let's go ahead and just figure out, well, how can we can think about the base case as being when width is less than or equal to 10, because that's going to be the case when we don't recur, right? We just have an implicit base case here. And so to get the width to being less than or equal to 10, we can decrease some amount of width, right? So one option here would be I could decrease width by 2. And this wasn't what I asked you to do, but we can prove to ourselves that this works. And this gives us a very uniform looking decrease in width each time we make our left turn, right? But if I were to multiply this by some percentage, we could achieve a similar result. However, as we move through this, we'll get a slightly nicer looking graphical pattern, because when we move further away, our lines are getting closer together because the percentage is causing a smaller decrease in the length of our lines as we move closer to the end, right? So notice how they're getting closer together. And that gives a very nice, almost 3D feel, right? We could make this a bit bigger. I could say 200 here. And I could also increase my speed to be much faster, so that this is a little bit more exciting to watch. And you can kind of get the sense that, wow, we're making some interesting graphics here just by taking some very simple process and repeating it recursively. Right? So I mentioned what if we wanted to have an explicit base case? Well, one of the ways we could do that is if we rewrite our logic, right? So this is an if then else statement. And we could think of the else as being our base case, right? Do nothing. And one of the things we should remember about writing code is that if we have some condition like this, we can invert it, right? We can think about this code from the other angle. And it's been a while since we've thought about if then else statements explicitly. We've kind of taken this as assumed knowledge, but we know that this is true. This case will be reached when width is less than or equal to 10, right? That's the opposite of this. Okay, so how do we reverse this logic? Well, I'm going to say if width is less than or equal to 10, and then I'm going to cut our previous then block content and paste it below, and cut my comment and paste it above, right? And so what we've done is we've just rewritten this logic such that the base case is first, which follows the style pattern we've been using in 110 this semester. But programming style is really something that is a convention left up to the programmer or the team the programmer is working on. And one of the reasons for choosing style is to make it feel a little bit more approachable when you are looking at some code for the first time. If that code was written using some style guides you're familiar with, in this case, one of our style guide expectations is that we provide the base case first. We have an easier time processing this. And so as humans, processing this as humans. And so we can take a look at this code and recognize that, hey, okay, a spiral is when the width is less than 10, it's just going to do these two things and not recur. But when it's greater than 10, we're going to spiral and decrease the width by 3% each time we make a turn. All right, so this is an introduction to turtle graphics. And in this sequence of videos, in this sequence of examples, we looked at how do we draw a square. And that was trying to illustrate how do we take some very simple, primitive things that we can do and start to express bigger picture ideas from them. And then here in Spiral, we're looking at how do we define a process recursively in terms of itself. And notice that with very little logic and code, we're able to achieve some pretty amazing things. So we're going to take a look at another example that will also look at recursion from a different angle in the next video.